about this new technique that we have now in series. I'm sorry I'm speaking in English, but feel free to ask me questions in Spanish. I can understand. The only thing that I will answer in English, and also feel free to make questions during the presentation. It's okay for me. So let's start share my screen.
Aline, I need to start the process of putting the meeting in YouTube. Please let me give me a few minutes.
Okay.
Okay, you can start, Aline.
Okay. So again, thank you very much for the invitation. And in this class, I will talk about the new techniques that we have in series that we hadn't before at the UVX. So at series, you have this new property of the beam, that's the coherence, and these open new opportunities in science. And so the main topic of this class, it's gonna be how we can use this coherent X-rays to review dynamics and 3D structure in materials. Okay. Well, so I imagine that the main topic of this course is to discuss this techniques to characterization of materials. And we know that to design efficient materials, we have to be able to answer different questions, and they're not easy questions like what's the relationship between the function and the structure, and also how we can control the hierarchical structure of the material, how we can tailor the properties. And to be able to answer these questions, we need to combine different techniques and use advanced techniques. And in this presentation, I will show two main techniques that allow us to study the structure and dynamics of materials using these coherent X-rays in the synchrotron source. So I will talk a lot about dynamics and structure, but what dynamics I'm talking about? So the main dynamics that we'll be able to study with this technique, it is process like aggregation, phase separation, transitions, and the technique that allows us to study this process, it's called X-ray photon correlation spectroscopy, XPCS. So this is gonna be the first part of this class. And to review the structure of material, the 3D structure, we can use the coherent X-ray diffraction image, CDI, that allow us to have information about 2D and 3D morphology, the porosity, defects, the different phases of the material. And it's really nice because we have the information about the surface and also about the volume of the material. So we can have a lot of information that I will show you later in the second part of this class, and also give some different examples to make it clear. And I hope at the end of this class, I can convince you to use XPCS or CDI in your project. Hope that these techniques can help you to answer some important questions in your research. And also that's very important characteristic of synchrotron experiments. Well, for those who have been in a synchrotron before, have a lot of space and also have this high flux that allow us to use different kinds of sample holders and allow us to do these experiments in situ in operand conditions that are really important to help us to answer this relationship between structure and activity. So during this presentation, I also show some examples of these techniques in this for in situ and operand studies. So the most important thing of this presentation is coherent X-rays. I talked a lot about this coherent X-rays. I imagine in this course you already had the SACS class. So in SACS, we use a partially incoherent beam. And what we have, it is a diffusive scattering. I just change my pointer. Okay. So when I have this incoherent beam, this partially incoherent beam, we have this diffusive scattering. That is a measure of the average of the sample. It's very important to answer different questions about structure, size in the sample. If you illuminate the same sample with a coherent beam,
It's okay, Aline, you can continue, I think. Sorry for the delay.
okay, no problem. So when we illuminate the sample with the coherent beam, we obtain this speckle pattern. And this speckle depends on the exact arrangement of the sample. So have information beyond the average properties. And then I hope also I can convince people that are used to work with SACS that using almost the same experiment, I'm show later what it's different from XPCS and SACS experiment. It's basically the way we collect and analyze data, but in the same experiment, we can obtain the SACS information and also the XPCS if you have a coherent beam. So coherence. The main characteristic of the fourth generation synchrotron source as Sirius is the high coherent flux. So due to this new property of the beam that we have this high coherent beam, when we illuminate the sample, we have the effects of interference. So the coherent, what's the coherent beam? The coherent beam is the waves are in the same wavelength and the same phase as well. And then when we have the interference, it will create a constructive interaction or a destructive. When we have this constructive, we have a signal in our detector that we call a speckle. And we can imagine the main difference of this coherent and incoherent beam. I like this example. It's to imagine the one example of the coherent beam that we use nowadays. It's a laser point. In the laser, the waves are in phase, and when we have, for example, a lamp, we have these different phases and also wavelength. And when we illuminate the sample with this coherent beam, we obtain this speckle pattern. This speckle pattern, it seems random, but actually it's related to the exact spatial arrangement of the scattered object. So, for example, in this simple illustration, it's like we can imagine it like a colloidal sample. For example, each colloidal particle will scatter in this X-ray in one direction and will create one speckle. And then if we can retrieve the phase of this pattern, we can obtain information about the exact arrangement of the sample in the coherent diffraction image, for example. And in XPCS, we'd like to understand the dynamics, so how things are moving. So if we follow how these speckles are moving during the measurements, we can have information about how the sample is moving, and then what the kind of dynamics we have in the sample. So I start with XPCS, X-ray photocorrelation spectroscopy. So in this technique, we have different image speckle patterns of the sample. And as we want to follow a dynamics and movement, we will get a lot of images with a very short time between them. So we can imagine it like in this illustration, for example, it's a colloid, and we have one image like a screenshot of the position of the particles at this moment. And then if I do the same 1 millisecond later, I will have another configuration, and then so on. And we can have information how what was this dynamic of the samples. So it's like doing a molecular movie. And using this technique, we can probe dynamics at the nano and the micro scale. So degradation, phase separation, transition. So how is the experiment of XPCS? So in a typical XPCS experiment, we will obtain a lot of images. So for example, here, in this short video, you can see we have this fluctuation of the speckle patterns. It's due to the fluctuation of the scattered species in the sample. So we're gonna take a lot of images, like thousands of images, with a time between them that can go from milliseconds to seconds to minutes. It depends how fast the dynamics of your sample. Then we're gonna choose a region of interest. So the same thing of SACs. So we're gonna choose a Q vector range, a Q vector region, or several Q vector region. Then we will obtain the intensity of these speckles in this region that is selected, and we will apply the intensity correlation function. So we'll correlate this sample, this image, with different times. So we correlated all the images with a delta t, then all the images with 2 delta t, 3 delta t, and we will construct this correlation curve. So this is the main result that we will obtain in this technique, that it's this correlation decay that gives us information about the sample. So when we have the correlation of 1, so what we were correlating? We're correlating the different images. So we're correlating the initial position of the sample with the final position of the same particle. So at the beginning, the correlation, it's 100%, because the sample, this particle still do not move. Then when the particle starts to move, we observe this decrease in the correlation. And at some point, it's too far. We do not have any correlation anymore. And the shape of this curve is gonna give us information about what was the mechanism of the movement of these particles in the sample. So, how we interpreted this correlation function data? We always have exponential, most of the time we have this exponential decay. The maximum of this exponential decay, it is the speckle contrast. So it's related with the beamline configuration, with the beam, the coherence of the beam, also the detector properties. we obtain a very important parameter that is the relaxation time. And then we can use different expression model to obtain more information about the dynamics in the material. So based in the shape of the exponential decay, we can have this different relaxation process. So then first we calculated the correlation function, then we can fit this exponential with different models. The most used for soft matter, it's this QWW expression. From this fit, we can obtain the gamma, and this will give us information about the nature of the relaxation process. So, for example, if you have a single exponent, so gamma equal to 1, it means that you have a single relaxation time. It's a free diffusion, so it's characteristic, for example, of a Brownian motion. If you have a stressed exponent, we have a distribution of different relaxation times, so it's very common in subdiffusive motion. And when you have a compressed exponent, we have an internal stress relaxation, so it's very common to be observed, for example, in gels, polymers, and it's characteristic of superdiffusion motion. So we can, the most important results that we obtain in these techniques, it's the relaxation time and also the nature of the relaxation process. As I told you, can quantify these dynamics using different models. So, for example, we can obtain the diffusion coefficient, and then we can obtain more information about the hydrodynamic radius, for example. And we can also use this expression to obtain the information about the gamma exponent and also the relaxation rate, the relaxation time. So, well, I think things gonna be more clear when I show some examples. So I chose different examples. Most of them are related with soft matter, because here at Sirius we are performing XPCS in transmission mode. So it's really like stacks. But we can also perform XPCS in wide angle reflection mode, like wide angle scattering, so wax condition. It's used more for to study metals, hard matter. So in this presentation, I will focus more in soft matter because it's what are available now in Sirius where we start to work. So first example that I choose to show you, it's part of my own research actually, is how we can use XPCS to understand the gelation and phase separation process. So in this project, we use sol gel methods to produce gels, and we combine phase separation to produce the porosity. So this system, it's a very complex dynamics because during the gelation, we have network formation. So have this dynamics, and then things start to be arrested during this network formation. So it's very difficult to study this dynamics using different techniques, and then XPCS can help us to understand this process. Another very important characteristic of XPCS that is we can cover a hierarchy of length and time scale. So we can cover a length scale from nanometers to micrometers, like from few nanometers to hundreds, no, not hundred, sorry, few nanometers to tenths of micrometers, and also a very broad time scale. So nowadays at CATT, we can cover from milliseconds to minutes, hours, depending on the material. And this is very important, for example, in this case of gelation. At the beginning of the process, dynamics, it's very fast because you have like small clusters. As these clusters are forming this gel network, the dynamics slow down. So it's important to be able to follow this fast and also slow dynamics to have the whole process. And for the length case, the same thing. Things usually start the small particles, small clusters, and then they can grow, and then we can follow this evolution using XPCS. And comparing with other techniques that allow us to study dynamics, XPCS, it's very close to dynamic light scattering. So who had worked with DLS, it's very similar. The difference that using X-rays instead of visible light, we have some advantage. So we are not limited to transparent samples. We can have colored samples, opaque, even gels. And also using XPCS, we can cover a different length scale. Sorry, I'm a little bit sick. Hope my voice will be able to go to the end of this presentation. And comparing with inelastic X-ray scattering, for example, XPCS cover almost the same length scale, but we can study actually slow dynamics using this technique. So just to have a comparison between the different techniques that can also provide information about the dynamics. So in this project, we use the soft gel method that it's a really nice synthetic approach to design tailored properties materials, because we can control the properties of the material, change the synthesis parameters. We can also add some different materials during the gel formation, and in this example, it was to produce catalysts. So we can add the activity species during this gel formation of the support, and we have a catalyst, a supported metal catalyst in an oxide, and only one step, like one whole synthesis. And this technique has several advantages. We can use like room temperature, no need of pressure, and at the end we can obtain a material that is high dispersed, stable, and high homogeneous. But during the gel formation, we know that the microscopic organization and mobility of these species to form this gel network will control the final properties of the material. And when we include, for example, this metal species during the gel formation, it can change the way these particles will connect to form the network. Depending on the concentration, it can really not allow this homogeneous network formation. We can have segregated domains. So it's important to understand the dynamics of the gel and also the dynamics when we include this metal, how it's going to change. And to make things a little more complicated, we also like to have a porous material. So we combine phase separation with soft gel transition. So for this, we can add a polymer during the social transition that will induce phase separation, the spinodal decomposition, and then we will obtain a gel-rich phase and a solvent-rich phase. Then we can remove the solvent drying and by heating, and you have a porous material. So we can obtain this really nice morphology here using this method. We obtain this monolith that's really nice for catalysis, for example, because we already have the reactor. It's a monolith reactor. We can control the porosity, controlling this polymer. And the idea is also include the metal and still have these two processes going on, the gelation and the phase separation. The phase separation will control the morphology and the size of the pores. So during the phase separation, we have an increase of the separated domains. And the gelation, when the gelation occurs, it's like freeze the system. And then we can keep this structure and produce the porosity. If we stop the reaction, if you have the gelation at this point or at this point, we will have different morphology. So it's a dynamic process that controls the final structure. So we are interested in understanding the dynamics and the kinetics of this process to be able to control the structure and have the different sizes of pores that you want, for example. So for this, we combine USAGs and XPCS in the cathetative line. We study this in situ during the formation of this gel and the phase separation. We have a capillary cell with temperature control that we can control, can cooling down and also heat the sample. This is all in vacuum, like stacks. Now we develop also another systems that's not all in vacuum. At XPCS, we do not have to subtract the background like we do in stacks, because in XPCS, we are interested of the movement of these speckles. So it do not matter if you have a background of air, for example. If it's not moving, it will not affect the result. But for sure, if you have like a large gap and then we increase the signal of the sample, then starts to become a problem. But if you have a small gap, if the sample is a good scatter, we can work with, we do not need to work in all vacuum. So just show nice microscope of this system that I think it's really nice. Here it's an example of the silica gel that we obtain only using this social method. When we included this polymer to produce the phase separation, we have this really nice morphology with this large macropores of 600 nanometers that are really interesting for catalysis to allow the diffusion of the chemicals in these pores. And also we can include the metal in this work. We included the nickel, and we have a well-dispersed nickel nanoparticles in the gel phase. So we went to Caterité to study these materials. So some characteristics of the beamline. At Caterité, we have this large detector per mega with a small pixel size. The large detector is not for XPCS, it's for image. Then I'll talk more about this later. But for XPCS, it's very important this information have small pixel size. It's why? Because it's important that the speckle, if you have small pixel size, you have a better resolution to resolve the speckle patterns. Also, we work at long sample detector distance. like 50 meters. And here at KTT, we have this large tunnel. The detector is inside. And we can work with broad sample to detector distance. It's from around 2 meters to 28 meters. So for XPCS, it's very important because when we have this large distance, we increase the speckle contrast. We can resolve the speckles better. Then we can increase the signal of the sample. And it's also important for USACs. So if you have, in this case, like this large macro pores, 600 nanometers, then we can have information about the structure using this sample this long sample to detector distance. At KTT, we have a beam size of 40 micron, and it's high coherent beam. What we do here at the beam line, we choose only the coherent part of the beam. So we clean the beam to get the coherent part. And in this experiment, we studied the sample there was at 40 degrees, and it's a very slow transition. So we studied during 360 minutes to have the whole history. So here I show you some results of the XPCS at the late stage of the gelation. It's why, because at the beginning, the early stage of the gelation, dynamics too fast. So we do not, in this first experiment, we focus in the late stage of the gelation because we would like to have information about the gel point and also the phase separation. So here, on this black curve, what you see that dynamic it's faster than we are measuring. So the decay in this region it's below a second. Then as time the sample the gelation is going on, this process starts to slow down, and we can observe that the dynamic it's slowing down. So each curve was taken between 10 minutes, and we follow during several hours, taking this image at each 10 minutes. So we can observe the dynamic slow down in the late stage, and it's expected because it's this constrained motion of the clusters that are forming this gel network. So here I selected one curve, this of 330 minutes. And as we have this 2D detector, we have the information in a large area. So we choose actually different Q vector to analyze the sample. And we can have interesting information when you fit these results, and we obtain the gamma exponents, the relaxation time, and we observe how it's the Q dependence of the relaxation times and the gamma. It's gonna give us more information about the dynamics. So here we can observe we have a relaxation time that decrease with Q, and also have this gamma exponent that is above 1, because here we have the decay characteristic of a stretched exponent of gels. Sorry. So when I have this gamma exponent higher than 1, and also the relaxation time independence of Q, following a power law of -1, it was observed in soft materials, in gels. We also have a lot of different systems where we can observe the same behavior. And this is, with this, we can conclude that in this case, we have an hyperdiffusive motion. So we have this relaxation of heterogeneous internal stress. What stress? This is stress that is built in during the cluster aggregation to form the gel network. So the dynamics that we are observing here is this stress, this stress of the network itself, how it's as the gelation is going on, the network become more rigid, and then we can observe the difference of the stress of this network. So look into this one-time correlation function that we called these results. We can have this information: what's the characteristic relaxation time, what are the nature of the relaxation process, what type of dynamics. But sometimes we have heterogeneous dynamics in the system. The gelation is one case, because you can imagine, as we are talking about this network formation, as the network formation it's going on, dynamics starts to become slower. So we have heterogeneous dynamics. So in this case, we cannot only analyze and use the one-time correlation, because in the one-time correlation, we have an average of the intensity for the same delta T. In this case, when we have heterogeneous dynamics, not the most correct, we can use this another analysis that's called two-time correlation, where in this case we correlated all the one image with the first image, and then correlated all the image without any average. So if you have heterogeneous behavior, we can have this information. So for example, if you have a system that's going from a state A to a state B, C, D, we can have this information. So here have typical results that we have obtained for this two-time correlation analysis. We have this two-time correlation map. If the system is in equilibrium, so it's the correlation with the image with the sequential image. If the system is in equilibrium, have parallel lines, not going on. If you have the system is slowing down, for example, the case of gelation, we observe an increase of this region. And it's the opposite when you have an accelerated process. For example, we have a diffusion that's, I don't know, dynamics, it's becoming faster. So we have this profile. So using this two-time correlation, we can have more information about aging, for example, aging of the gel. So here we have the two-time correlation for the same system that I showed you before. So around 300 minutes you have this parallel line, because the system is still in equilibrium. Things are too fast. As the gel network is formed, then starts to slow down. We can observe this profile. We can observe the gradual slowing down of the dynamics, and the network fluctuations becomes greatly suppressed, and at some point we observe it's increasing, and then at the end it seems starting to become in equilibrium again. So we believe this is because we had this phase separation of the same time that we had the gelation, because During the gelation, you have this increase, this evolution, the formation of the gel network, and at the same time, the phase separation. Once you arrive to the gel point, it's freezing, the phase separated inside. We have a equilibrium system again. Its things are really, really arrested there. They do not have many motion. So it can give us information about when it occurred. So it's also interesting to observe how the relaxation times increased with the time of the analysis and the gamma as well. And we can observe we have a jump after 320 minutes when the system starts. It comes from a more the clusters are still more free, they can move a little bit faster. So gamma, it's around 1, it's almost like a Brownian motion. And then when it starts to slow down to become a gel, we have a gamma above 1. So we can observe this transition from straightened to compressed exponent. And during the same experiment, we also have the USACS information. That's really nice because then we can combine dynamic evolution with structure evolution. We can understand better our system. If you observe the SACS, we start to see here that we have the growth of these particles. So we have this flat region that's grown intensity, and also it's moving to smaller Q region, and around 300 minutes we have an important transition. So observing the duration radius, you can observe that at the beginning you have the growth of we have a slow growth of the clusters, and then at 300 we have this phase separation, the gelation, and we have this jump in size, and we form these big structures that most probably is the macropores that are formed during the phase separation. And then we have this slow evolution that it's related with the coursing of this phase separated domains. So combined, what we believe at this point we formed this structure. And so have this slow dynamics, we can observe the gel network formation and then the coursing of these phase separated domains. So this was first results that we obtained in the systems. Controlling the polymer, we can control the morphology, and now the next steps is to understand better the whole. Actually, I already have these results about, we could see how the metal changed a little bit the dynamics, but we still have the macropores, and also understand how using these different polymers, how it change the dynamics, and then understand better how we can control this dynamic and structure formation. We can obtain more and more controlled materials, depends on the application. Do you have any questions and any comments? Are you still with me? Okay, so I keep going. If you have any question, feel free to ask me.
Aline,
the evolution of the time 1, like the time 1 with the time the time too. It's like time by time. You have this map. It seems time by time how things are correlated with during the whole measurement. Then it's in equilibrium. It's always correlated. I have only this parallel line.
Okay.
If things start to be slow, this region where we have the correlation, it's gonna increase because things are really slow. So it's already correlated in this region, and then when time's going on, things are becoming slow. It's correlated more and more. So have this characteristic profile. That means things are slowing down.
Okay. So you do that for every time that you take one image and you perform the correlation between those.
Yeah. So for example, in this example, we collected like 1,000 images, one image per second, for example. So here we have 1,000 seconds by 1,000 seconds, and then we observe how it's correlated during this.
Okay.
This time by time.
Okay, and there I have another question. In this example, you perform one USACS experiment and one XPS experiment at the same time.
Yeah, actually it's the same. So what we do? Yeah. So during the XPS experiment, during the SACS experiment, for example, we obtain one image, I don't know, 10 seconds, 1 second, 6 seconds. Okay. We integrate it, obtain SACS curve. For XPS, I need to take a lot of images to be able to correlate it, the speckle pattern. So for example, in this specific example, we obtain 600 images, 1,000 images, 1 image by second. And then we can obtain the facts from the same measurement, averaging this image.
So you average the XPS experiment to obtain the USACS curve.
The SACS, yeah. So this is the nice thing, that it's really you have both in the same shot, like the same. So we have the scattering, we have the speckle pattern, we analyze, we autocorrelated, have XPS. We average and we integrated the USACS curve for the same set of data. Okay. And this allows us to correlate it really well, the structure and the dynamics.
Perfect. And you also show one image of the correlation scale time for this experiment. It was I think the previous slide. And you talk about that at the beginning, the information that you need, this one, the black one. So all the dynamics occur in a time scale that you cannot reach.
Yes, actually, it was not that we cannot reach. We can. The maximum we can measure at cathedral takes 1 millisecond. Okay. The thing is that it was like the first experiments we are learning about the systems, and I choose to obtain this image in this slow mode. It's why I didn't get the faster dynamics. But actually what we implemented now on the beamline, that's really nice. We implemented a new script that we can obtain both. So for example, at 10, I take 1 point at each 10 minutes. So I take one set of data of slow dynamics, like 1 image per second. And then we can obtain a fast set of data, for example, 1 image at each millisecond. Okay. And then you have both slow and fast information, and so then you can analyze.
You can get the 2 time scales in the same experiment.
Yeah.
Almost the same. Okay.
And it's very useful in the beginning when we are learning more about the system. It's very, because sometimes it's hard actually to have information about what's the time scale of the dynamics in your materials. Usually,
invisible, you don't know. You know, it's like
you don't know.
what it is.
Okay. It's really hard. For example, it's easy when you have Brownian motion, like big nanoparticles. You can estimate, for example.
Okay.
But for more complex systems like this, you cannot. So what you do on the beamline, the user arrived, first thing, we're gonna test some time scales.
Oh, perfect.
To try to find out if the dynamics, it's in millisecond range, it's in second range, it's minute range. So we do this first and then start experiment. But for the in-state experiments, it's more difficult because it's a long experiment. So what we did, we chose one and tested it. For next experiment, we will try to get the fast dynamic.
Okay, thank you. Chicos, ¿alguno de ustedes tiene alguna otra pregunta de este primer ejemplo? Pueden abrir los micrófonos si quieren y preguntar en castellano, que Aline entiende.
So this next example, I will show it's an example from a user that we have here. They were interested in study phase separation in protein solution. The phase separation, it's like a natural mechanism that occurs in the cells. It's used to organize the intracellular organization, forming the biomolecular condensates, but it's also associated with a variety of diseases. And it's really hard to study the system because it's the same, it's close to the gels because it starts from few proteins that can aggregate, can form a gel, can form a solid. So we have this broad time and length scale. So we use XPCS to try to probe the mechanisms of the relaxation behavior of this protein condensates. And these proteins that they studied that's related with several diseases, they know that the phase separation is induced by different ligands, in particular by copper. So if you look here, the optical microscopy, for example, when they add copper in these proteins, you can see the droplets of protein condensates. And if they add, for example, copper and peroxide, they obtain completely different morphology that's more a gel network. And this occurs naturally in the body, in our body. So at some point we have more peroxide and you change this protein condensate. So they came to the beamline and we studied this. We mixture these proteins with copper and copper peroxide and we analyze the dynamics. So what is interesting to observe that you have different profiles, the correlation curves profiles depends on copper or copper peroxide. In both cases, it is small dynamics, analyzing the evolution of the relaxation rate with Q and also the gamma exponent with Q. We can observe we have different relaxation process in the systems. When we have only copper, we have a subdiffusive relaxation that it's related more with the coarsening of these droplets because it's formed these droplets, and as time goes on, they start to fuse. So have this coarsening of these droplets and adding peroxide, we have because when the protein forms this condensate on the cell, and it still has like a liquid property, sometimes it can reverse the body, the cell can reverse the process, and then the protein is free again to do the function in the cell. When you have this the formation of gels and solids, sometimes it cannot be reversible. So you lose this protein, and you also form solid particles inside the cell, and then it will induce the death of the cell and cause the disease and so on. So it's very important to have this viscoelastic information, and then also information that you can obtain using XPCS. So in this subject about protein solution, we have some recent works. People are discovering that XPCS can help giving us this information about this viscoelastic properties that is very important to understand if the protein will be still available in the cell or it's formed the solid gels, and how it's going to influence the disease itself. So in this is work from literature. They were interested in understand where this phase separation is occurring. It is in spinal region, or it's formed this spheres, because it's also important to understand what's the morphology of the protein condensate. First of all, they analyzed the site data, and they could observe the spinal peak. And in this case, it was also important to them to analyze both the two-time correlation and the one-time correlation. Looking at the two-time correlation, we can observe like three different states. First one, we only have this parallel line. Dynamics is too fast, the systems are in equilibrium. Then we can observe dynamics start too slow, and then it's really slow down, and depends on temperature. It's occur at different time. And when they observe the one-time correlation, they can observe the same thing. We have the dynamics. It's moving for a long time. It's slowing down. At some point, it's arrested. You see, we even do not have the whole decay, because it's really the system was completely arrested at some point. So analyzing the evolution of the relaxation rate in function of the time of the experiment, what they observed that is the early stage of the spinal decomposition, the dynamics increase with temperature, so it speeds up with temperature. But then at the late stage of the phase separation, they observe the slow relaxation rates. So at lower temperatures, relaxation times are larger than the higher temperatures. So due to these results, they want to have more information about this spinal decomposition process. They simulated how it's gonna be this spinal decomposition using the Cohn-Hillard equation, and then it was really nice because they could simulate the one-time correlation, two-time correlation. Depends on the stage of the spinal decomposition, and it fits really well the experimental data. Then they could understand better the three different stages of the dynamics. So the first stage, it is the beginning of the spinodal decomposition. So it's the formation of the interface between these two different phases. So we have this very fast dynamics. Then at the second stage, you have the growth of these domains, like represented in this illustration. And at the end of the dynamics, the third stage, they observed it's the coursing of this separated phase. So they could have more information about the mechanism of the separation of this protein. And they also observed that the spinodal decomposition was controlled by the mass transport mechanisms and mobility of the components. I think I will give one quick example, and then we can have a break. This is, I think it's, at the beginning I thought it was a little funny, but it's really nice to show how using this technique we can understand processes that are more complicated than when imagined. So in this study, they studied the gelation of the protein of an egg. So they buy an egg and they fry this egg, and they study this process that we observe every day in our house when you fry an egg and have this formation of the white egg. Actually, they focus this study in the gelation of the egg white. So it's interesting because during the gelation of proteins, we know we have denaturation, that's heated induced, and also we form this three-dimensional network structure. So they observe at the beginning of the gelation, everything was too fast, they could not observe anything. Because they believe that this first point is this heated induced denaturation of the protein. Once the protein is denaturated, it starts to form this gel network. So here we start to see a slowing down of the dynamics as the protein starts to form the gel, and then we have a slow down, and then it's become faster again. So we have a fluctuation of the dynamics. So have really heterogeneous dynamics in the system. So to understand better what's going on, they analyze the evolution of the gamma exponents and also the relaxation rate with time. So we can observe for the first, in the beginning, we have an increase of the relaxation time with the increase of the experiment. And at some point, it becomes constant. This first fast stage, it's related to the stabilization of the gel network that was freshly formed. Then, as the network is going to be formed and have the increase of the cross-link, it's accumulated stress in the gel. And then when you have this fluctuation, that system becomes faster and slow again. It is the fluctuation of this stress of the gel network. As we know, when you have this white egg gel, it's soft and it's flexible. And then we have this fluctuation that it's like to accommodate the stress of the newly formed gel. And then they could see it's a structured event that occur when this network is formed. So the gelation of the proteins will start when the electrostatic repulsion between the proteins is reduced after the heated induced penetration. Then the gelation, they identify the stress driving dynamics as the dynamic rupture events, where you have this fluctuation, this restructuration of the network, but it's just we are just talking about the stress, accommodating this stress. It's not changing the structure. So it was, I think it was interesting to see. It's such a simple thing that to observe every day, but there's a lot of heterogeneous dynamics going on in this formation of the white egg. So these were some examples. I choose more these examples that were more related with gels and proteins that are subjects that I work more, but XPCS can be widely applied in colloids. So it's very interesting to understand colloids, Brownell movements, how it changes depends on the composition. So this is an example for magnetic colloids where they control this magnetic colloids with a magnetic field, and then they can observe how it will control the motion of the particles. As I show you, we can use to study gel formation. We can also use XPCS to study composites. So, for example, to study a polymer, and then we add a composite in the polymer, how it will change the behavior of this polymer, if it becomes more rigid or soft, and for sure it will affect the dynamics, and using XPCS we will be able to have information about it. Lisandro, I think we can have a break now.
Okay, as you wish.
It's okay.
Yes, of course. Let me pause the...
What we expected in these experiments. So for the XPCS experiments, the first question we will ask you is what time scales are we expecting? I know it's hard to answer this question, but at least you have to have an idea based on works on the literature, similar systems, to have this first idea, because then in the beeline we start to test. But for example, if the dynamics is too slow and we start to test only fast times, we always have like flat, not any decay, because the decay is in another region that we are analyzing. So it's important to have at least one idea to find out quick what's the characteristic time scale of your system. When it starts to try to analyze, and for example, we start to see like just the beginning of a decay, it's perfect enough. We start, okay, it is lower than we thought, and then we can increase the number of images. It can be one way, or we can increase the time of the image. So there's different approach we can test. Another very important question, it is radiation limit. Because here in studios and in the fourth generation synchrotrons in general, we have a really high flux, higher than we had before. So samples that sometimes people do not have problem before doing stacks. Here we start to have radiation damage during this high flux. So it's important to think about radiation damage, how your sample will behave, it's sensible for it, because then we can try to find out some approach on the beamline. What we use most, it uses some filters to decrease a little bit the flux and then be able to measure. Because the main problem, it's radiation damage, a combination of samples that are sensitive to the beam with slow dynamics, because then we need to measure for a long time. So for example, in this case, it's fast dynamics, the relaxation time is below 10 seconds, but if the relaxation time, it's like, I don't know, 3 minutes, your sample have to spend on the beam. Then we can also do some, we can change a little bit the experiments. For example, we can obtain very, very slow systems. For example, 1 image per second, but instead use exposure time of 1 second, exposure only 10 milliseconds, for example. Then exposure 10 milliseconds, we wait, and then we collect another image. There are some strategies that we can use to work with this radiation damage, but it's important thing. We have to thinking about it, and also during the experiments try to check this, because also the worst thing for XPCS is that radiation can induce dynamics. This is the worst part, and you can imagine, for example, I don't know, nanoparticle like a colloid, and if the beam induced aggregation, you see a dynamics characteristic of aggregation, but actually the beam induced aggregation. And then will lead you for a wrong interpretation of your system. So this is a very important point in XPCS. Also, an important point, same for SACs, how much does the sample scatter? This sometimes it is a problem, because if the sample do not scatter well, we do not have signal, and it's a fast dynamics, the exposure times are really slow, like 1 millisecond. So it's a very important point as well. This you can have an idea before come to the beamline. So I already did any experiment using X-ray, you already have an idea. And also very important during the XPCS experiment, be able to analyze the data quasi.
Okay, you can continue, sorry.
Okay, no problem. So this last point, it's related actually to the first one. As I told you, it's really hard to know exactly what's the time scale you're expecting for your sample. So we need to test on the beamline before start. So for this, you have to be able to analyze the data and plot this correlation function. And then we're gonna have an idea, okay, you have the whole decay, or oh, it's missing still one part. We need to obtain more images, for example, or increase the time. So it's very important to have these tools to quickly analyze and look to the results and decide if it's good enough, if you need to change something on the experiment. And when we're talking about XPCS, actually we're talking about a lot of data, because you can imagine, for example, if we have a fast dynamics, in this example here, it's the dynamics of gold nanoparticles. So we obtained 1,000 images with 1 millisecond. So in 1 second, we obtain 1,000 images. This whole data, it's like 36 gigabytes in 1 second. So we are talking about big data, produce a pipeline that allows us to deal with this big data and reduce the big data and show a result. So it's a little bit challenge, but we are working in this, and we already have these tools. So when we come to the beamline, we'll be able to see the results. It's still taking a few minutes. Now we need to decrease even more this processing time to be able to see the data and take the decisions during the measurements.
Aline, one question: is there any? Do you have any other technique that you can use to test all of this, like the time scale, before you came to the synchrotron? Is there any
For
that you can do?
So if you have like a colored system that it's transparent, you can use DLS.
Okay.
That will help a lot. If you have like facts kinetics of your systems, you already have an idea as well when you have the chains.
Okay.
But there's not many actually, so sometimes it's complicated.
So
It's
in
why
principle,
also
you
helps a lot.
okay. In principle, you get you go there like a little bit blind. You know, it's like you have to go there and test the sample. Okay.
Yeah, what I advise the users, it's always to take a look on the literature, try to find similar systems that use the XPCS, then it's give a good idea.
Okay. 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 Perfect.
And then this is gonna be for the first time, and then well, once you learn what's the time scale characteristic of your system, then it's really nice for the next experiments. It's gonna be quicker to start.
Okay. And another question about the beam damage. So you need to check the beam damage first in order to see what is the time scale that you have to use for your experiment. Okay.
Yeah. So we have different approach. First thing, we do like sacks, fast sacks, because if you have the dynamics and your sample are not, you do not, it's expected to not see any change on the sacks profile.
Okay.
So for example, for colors, I imagine my sample has a time scale, I don't know, of 10 seconds. So I collected the XPCS data using 1 millisecond exposure time, and I plot all the sacks curves first. It's not expected to see any change. If we start to see, for example, an increase of the sacks curve, it seems it's one. It's related to the increase of the sample. So for sure, it's aggregation, for example.
Okay. Okay.
Or if you see any change in the shape of the sacks curve, so it seems it's happening, it's changing on your sample. It's the first approach.
Okay.
It's the easiest one. You collect one XPCS data and you look at the sacks curve, because you do not expect evolution of the structure, because you are interested at this point at the XPCS evolution of dynamics, not structure.
Okay.
Then the other thing we can also do, we collect XPCS and you have the decay here, for example. You see, this decay, if we started to collect it 1 second, we have part of the decay. So we change a little bit the time scale and we collected different conditions. And all the decays should match. If they match, for sure they're coming from the sample.
So
if
you check if there is any dependence of the time scale with the flux, for example.
Yeah.
Okay.
This as well. And then if you start to see some change,
you are in problems.
It came from radiation, yeah. And then when we identify radiation damage, we use these filters, these attenuators, to decrease the flux and try to find a good condition to work without radiation damage.
Thank you. Yeah.
So at the beginning of the XPCS experiment, we spent sometimes in this process. Find the time scale, find the radiation.
To be sure that you are in a good condition to perform the experiment.
Yeah. Okay. Once you find these conditions, okay, ready to go. Okay. But at the beginning, you have to use some time of the beam time to find these conditions.
Thank you.
So some information about the cathode beamline, the beamline that I'm working. So the cathode beamline is dedicated to coherent and time resolved scattering. So we can work with energy from 5 to 20 kV. The coherent flux is quite high, and the beam size we have this opportunity to change, but usually we are using fixed beam time like the large beam, because for XPCS it's also really nice to have a large beam because we decrease the density. Now if you have a bigger spot, so it's better for the sample that can suffer from radiation damage. And well, I think the more impressive thing of cathode when you visit it for the first time, it is the detector tunnel, because it's a huge tube of 30 meters, and the detectors inside is in vacuum, and we can change quite easily the sample to detector distance. Not changing during a measurement, this no, but for example, if you have even for the gels that I show you first example, if I'd like to focus in the early stage of the gelation or the late stage, I have to change the detector distance to cover like this few nanometers species, and then go to this micrometric species, for example. In this case, you have to do like 2 experiments in the same system if you want to do this. If you have systems that you already know, like, I don't know, colloids that you know they have different sizes, you can choose to start at one sample to detector distance and then move to the other one to optimize this. It's possible to do. So at Cathode, we have 3 main techniques. The coherent X-ray image, that's going to be the next topic of this class. XPCS that I showed you some results obtained at Cathode, and USACS ultra small angle X-ray scattering, thanks to this huge tunnel that allow us to use this sample to detector distance up to 28 meters. Just few details about the beamline. I'm not entering this in this technical part, but just for curiosity. So as I told you, is the coherence, it's a characteristic of the Sirius beam. So it is produced and it has a high coherence mode. What we'd like to do, what we try to do at Cathode, it's to keep this coherence. It's only cleaning the beam a little bit. For this, we touch the beam the less we can. So when you look at the optical elements of the beamline, it's quite simple. We have 2 mirrors, one for vertical focus mirrors and one other one for horizontal focusing. We have the monochromator to select the energy. We have the vertical coherent slits to select the vertical, to clean the beam in the vertical and the horizontal, and then keep on the coherent part of the beam. And then at the experimental hutch, we'll have slits just to clean the parasitic scattering. And this beam will, you go to the sample, and then we have this scattering from the sample that will be acquired by the detector inside the tunnel. So we try to touch the less we can to not lose coherence, because, well, anytime you touch the beam, you change, you lose a little bit. So the idea of Cathode is to take advantage of all the coherence of series. And another interesting element of our beamline is the detector. It's a pi mega detector that is an in-house joint it's a development in-house jointly between Sirius and a company from Campinas called PTEC. It's based in the MedPix technology, and you have this large area detector with this small pixel size, and it allows us to have a maximum frame rate of 1 kilohertz. So this is what limits our XPCS today. The fast we can go, it's 1 kilohertz because the detector limitations. There are some lines around the world that they have like special detectors for XPCS that they can go faster. But here at KTNT, we can go maximum to 1 kilohertz. That it is enough to study a lot of different materials, colloids, gels, different systems. And then for the slower rate, we do not have limit. It will depend on your sample, how long the sample can take radiation. So if it's a really slow dynamics, for example, a glass, but usually glass are quite resistant for radiation damage, so it's not a problem. You could measure for minutes, hours, there's no limit, but the fastest we can go with 1 kilohertz. And during this presentation, I focus more on slow dynamics, but we can, here it's a result just to show you a result using the maximum capacity of the detector, 1 kilohertz. It is gold nanoparticles of 400 nanometers diameter in a mixture of glycerol water. Here you have the Sachs curve. And then going back to the Lisandro question about the experiment. So it's not exactly the same. This image is not from the gold nanoparticles, but when we acquire XPCS, in this case, take one image each 1 millisecond. That's really fast. We only have like our speckles. If you average this speckle pattern, we will obtain this pattern. We cannot see the speckles anymore because we average and then we lose this speckle contrast, but it's not a problem. This is to obtain the Sachs. So this is averaged image from the XPCS experiment. Then we integrate it to obtain the Sachs. And here the colors indicate the Q range that we choose to calculate the XPCS correlation functions. So it's represented here in the sketching and here in the Sachs curve. So each color corresponds to the dynamics at one region of Q here in the curve. And how far you can go in Q region also depends on your sample. If your sample scatter well and you still have signal, you can have a broad Q range. If it's not a good scatter, you only have signal in the small Q, so do not have choice, will be limited by how your sample is scattered. So summarizing this first part, using XPCS, we can study dynamics over a large length and time scale. And it can help us to understand systems that are out of equilibrium and also heterogeneous systems. So I show more these examples of the gels where we can have information about the stress, the strength of this network, how soft it is or how it's becoming harder. In colloids, we can have this information about how was this motion. For example, I showed the example of the gold in water and glycerol. I played a little bit with the glycerol and water ratio, so it was really nice to see how I could control the movement of these nanoparticles and they become slower or faster depends on the viscosity of the system. And well, looking at the local dynamics, it can give us information about the global kinetics of the systems, and then you can understand better correlative phenomenon of the extended system. Well, so this was the first part about XPCS. Do you have any questions before moving for imaging? Sure. Another.
¿Alguno de ustedes tiene alguna pregunta, chicos? Pueden hacerlo por el chat o pueden hablar directamente. Parece que no. Están callados. Están callados.
Okay. No, it's okay, no problem. It is a lot of new information, but it's nice. I hope it's nice to give you an idea what we can do, what the techniques, what are these new techniques. So the second part.
Yo tengo I have a question, Aline, sorry, but I'm quite interested in what in your talk. If is there a possibility to perform this type of this experiment in one direction only? You know, like you have a flux of particles, and you can distinguish between the vertical direction and the horizontal direction in your image. Is it possible to do that? Oh.
Yes, it's really nice for, and I remember working with a system like this, for example. It's a cellulose sample. You have these fibers, so we have this different information in your scattering. If you are along the beam, if the fibers are along the beam or not.
Okay.
And then during the analysis, instead of choosing a circular Q range, you choose only in this different regions. So like we split your data into and analyze different portions. People have been doing this also for colloids under flux, because they would like to understand better the dynamics in the flux direction and perpendicular to the flux. Nice. So it's the way you analyze the data after, and we are developing this tool as well.
Oh, okay. Okay. Thank you.
Okay. So the second part, I will show you another technique that we have here available at Coherent, that is the Coherent X-ray diffraction imaging, CDI, that allows us to study 2D, 3D morphology, porosity, defect, phase distribution, and so on. In the Coherent X-ray diffraction image, we have 3 different techniques, but it's related to how we collected this data. So the first one, it's called plane wave CDI. So you see, it's the same thing as I showed you before. Using this coherent beam, we have this speckle pattern. As this speckle pattern depends on exactly the spatial position of the object on the sample. For image, what we're gonna have? We have an speckle partners. Each speckle comes from one part of the sample, and it's related with the position of one scatter object in the sample. So in this example, it was a cell. So for example, one it's coming from the surface, another from the mitochondria, and then we cover in the space of this scatter pattern, we can reconstruct the object in the real space, and then we can reconstruct the real object. If you perform a tomography, so it's like the tomography like in the hospital, what we do, we obtain one image of the sample, then we rotate the sample another image, we rotated another image, and then we will be able to have the tomography of this sample and then the 3D image of the sample. So this is the plane wave CDI. For this technique, the sample has to be smaller than the beam because the sample needs to be fully illuminated. So as I said before, at CATERET, the beam size is 40 micrometers. So this technique is limited to the samples below 40 micrometers. If you have large samples, another option is do tachography. Tachography, the difference is that instead of illuminated in a single shot the sample, we will scan the sample. So it's scanning this. So to construct this to the image, we're scanning the sample. Then we can obtain a 2D image. Then rotated, we can combine it with tomography and obtain the 3D object. And the other technique is when you have a crystalline sample. In this case, if we have a crystalline sample, we can collect the image around one bright peak. And then we're gonna have information about the 3D morphology and also the strength of this network that I show you later example of the tree. So let's start with plane wave. That's a really nice technique to study micrometric objects with nanometric resolution. So in this case, always keep in mind sample smaller than the beam. So this is an example from the literature. They studied yeast cell. So here we have the image from microscopy. We have really nice resolution, information about the surface. But these researchers were interested in studying what is inside the cell. So in this case, we can analyze the sample using plane wave CDI. And this is the reconstructed cell. Oh, sorry. Oh, my video is, it's a shame, but well, sorry. My video is not rotating, but it's just a video rotating this image. But here we can already see, the cell itself, the nucleus, the mitochondria, and some different composition of the cell. So in this case, it's a large object, I think it was like 10 micrometers, the whole cell, and they had a resolution of 50 nanometer that allow them to see these structures inside the cell. So they use a lot, not a lot, because all these techniques that I show in XPCS, CDI, as they need coherent beam, and the coherence is increased a lot with the 4th generation sync control. Their technique that they were performed before in the 3rd generation sync control, but they're developing now and developing more and more with these new sources as well, with the increasing coherence. So comparing with SPACs, for example, we can call them new techniques, because if you compare SACs, where you have Guinea in the 1930 developing SACs, the first speckle was seen in 1990. Oh no, sorry, the first XPCS experiment. So it's quite new comparing both experiment, image as well. So there are techniques there increasing application for different samples. And plane wave CDI, it's interesting for biology because of this possibility to study a micrometric object like a cell with resolution enough to see structures inside the cell. So another example of inorganic materials. So for this experiment, the sample is in the silicon nitrate membrane. We will obtain one image of the detector, and we will collect images at different angles to have the tomography. In this case, the samples were here some fragments of silicon, a porous silica sphere, and based on the difference of the density, we can also have information about about the density of the sample. So we can have information about the morphology and also information about the density. As it's a 3D image, we can cut and look inside and calculate it. If you have pores, the size of the pore connected, and I'll give more examples with the other techniques. So in plane wave CDI, is this, we can analyze biological or inorganic sample, have information about 3D morphology, and also estimated density. The technique that we are performing nowadays and are open for proposals at Coherent speckography, that is a variation of CDI. In this case, we scan the samples to obtain this 2D image. We scan the sample. So we are not limited by the size of the sample. We can study large samples, for example. And what we're gonna do, we will scan the sample, reconstruct a 2D image, then rotate it, and then we'll have the tomography. In this study, they were interested in study these photonic materials. So they produced these materials, and they use different thermal treatment to obtain the final materials, and they want to understand the effect of this heat treatment in the structure of the material. One challenge for imaging, I will talk a little bit more at the end of the presentation, but is to obtain this isolated sample. So we have to have an isolated sample on the membrane because we will rotate the membrane. If I have, for example, 2 cells, when I rotate, I will have signal from both. So this is a problem. So for inorganic sample, like I think most of us work with, there are different strategies. One of them is cut part of your sample using a focused ion beam, for example, a FIB. In this case, they use this to prepare. So they cut a part of the sample. Here is the reconstructed results of the sample before the heat treatment and after. Here, it's not easy to see the difference, but then we can analyze further this data. You have some programs that allow us, then once you have the 3D data, you use a technique that's called segmentation. That is, you're gonna separate the phases of the sample based on their density, in the scattering intensity, in the intensity of this reconstructed object. And here you can see they separated what was the macro pores that are represented in blue. Also, they separated this shell of the pores and also the core of the pores. And also, as we have this 3D image, we can have information about how these pores are connected. This is a really nice information for different applications like catalysis, separation. You can create this segmented results, separated the composition of our sample, and then we can use some models to calculate how the spore are connected, what are the size of the spore, with how many pores one pore is connected, how many closed pores we have in the materials. So we can have a lot of information about the material using this technique. Both of them for plane wave as well, because this, what I'm talking about now, it's the analysis. So if once you have a 3D image of a materials, we can perform different analysis. If the sample has pores, we can have this kind of information. So it's really interesting for catalysis. And we also have the opportunity to do this image in situ. So in this work, they produce the porous nickel alumina catalyst. They constructed a cell. We are also developing some cells here at Caterete to be able to study samples in function of temperature and with gases as well. And they study the calcination of the sample in situ using tachography. And here what we have, it's the 2D results only. So it's interesting to note, here is the sample, we can observe the pores. Once they start the calcination, we can observe the shrink of the sample. So they could follow this, and we know that this will define the final structure of the system. So we can follow this change in the sample. They also perform a 3D analysis of the sample. So here is the reconstruction. Here we can observe the macropores in orange, and in gray it's the material itself, the nickel and the alumina. Here it's a simulation, not a simulation, the result of the segmentation of the pore network. So it's interesting, you can observe how they are connected, you can separate it by size as well, how the large pores are connected with the smaller one or not. Then we can have information about macropores, mesopores, diameters, the porosity itself, the percentage of porosity, the connective, and also if you have like endpoint, if you have closed space, you can have information about it, analyzing this 3D results. And the other technique that I would like to spend a little bit more time.
Aline, I need to restart the meeting because of this time question. I
okay.
came back and keep recording.
Okay.
Sorry. You can continue, Aline.
Okay, no problem. So during this measurement, it's a very long measurement. So it's really different XPCS and CDI experiment. XPCS usually it's really fast. For example, if it's a colloid, you obtain 1,000 images in 1 second. So 1 second you already measure your sample. You take longer to go inside and change sample than the measurement itself. But tachography, it's like, it depends on the sample and the size, but it's like 80 hours, could be 80 hours, 6 hours, 10 hours to measure the whole 3D. Because of this, because I have to have a lot of projection. More angle you collect during the tachograph, better gonna be your resolution. So it's a really long experiment, and sometimes the sample can suffer as well of radiation damage. In this case, you can imagine, for example, I have a porous materials and it starts degraded because of the beam, because usually in this case it's more degradation that we observe. You start to lose information, but then when you put all this data together to obtain the 3D, you have a blurry result, because at the beginning you have could resolve the pores, for example, but then you have start to destruct the sample. So this is a problem as well for samples in Tycho, because it's a long experiment. Sample should resist to radiation.
Thank you.
And when we have crystalline materials, so we can have also this information that I just showed about morphology. We can do this analysis if it's porous, same thing, but have more information about also the crystallinity and defects of these materials. So just to introduction, why it's important to study defects, I will give an example in catalysis. So if you have a gold catalyst, for example, we know that if you decrease the size of the nanoparticles, the gold particles, we increase the activity. Because it's funny when you think about gold of catalyst, because we use gold in our daily life because it can resist very well to the reacted with for oxidation or anything else. But if you decrease the size of the gold produced these nanoparticles, we increase the activity. Why? Because we increase the defects and we also decrease a lot these low coordinated atoms in the corners of the nanoparticles. And in catalysis, the shape, the size will control the activity, but also the presence of the defects, what facet is exposed on the nanoparticle. And we know during the catalytic activity, the reaction, the chemical reaction will not occur the whole surface of our materials. It's going to occur only in the activity sites. And these activity sites, they are formed during the reaction, they have a short life, and we do not have many actually compared with the surface of our material. So if you want to have more information about where these activity sites are located, we have to be able to look to a single nanoparticle. So this is one of the motivations to use these techniques that allow us to study a single nanoparticle. So in bright CDI, same thing, almost the same thing of the image before. We're going to obtain one 2D pattern, diffracted pattern in this case. Then we rotate the sample and we construct this tomograph. But what happened when we illuminated a crystalline sample with a coherent beam? So the coherent beam, same phase. When we have a perfect crystal, it will be diffracted. We have one phase shift, but it remains on phase after the diffraction. If you have any defect on our sample, when we have the diffraction of this coherent beam, it will cause a phase offset in the diffracted photons, so diffracted wave. So this phase offset, it will allow us to give us information about this defect of the crystalline particles of our sample. If we do not have a coherent beam, it's not possible to have this information because we can already have phase offset on the incoming radiation. But working with coherent beams, the radiation is on phase. And if you have a difference of phase in the diffracted signal, it's for sure coming from the sample structure. So in this case, the difference in both cases that I showed before, plane wave and spectrograph, it's also transmission, it's the transmission setup of the beamline. laxates. They have the incoming beam, it's scattering, then collected by the detector in transmission mode. In the case of Bragg, we will position our detector in a position to obtain this diffraction pattern. So depends on what are your sample, the 2 theta of your sample, the peak that you're going to study, you position your detector in this part. So you have 1 2D diffraction, rotates the sample, another 2D diffraction, and then we reconstructed the 3D diffraction. In this case, for the gold, we choose peak 111, and we measure around this peak. So for this experiment, it was before series were ready. So we went to the US, to the APS. It's a work from a postdoc. And we studied these gold nanoparticles during the reaction. And it was really nice because we have a mass spectrometer on the beamline. Then we could study the results of the reaction as well. So it was an operand experiment. So here we have the sample, the reactor, the income X-rays, and here the detector to obtain the diffracted 111 direction. So we produced this shaped controlled golden particles using a colloidal synthesis. They're really nice cubes of around 60 nanometers. So here you can observe the microscopy image. Using Bragg CDI, we can obtain 3 main information: the morphology, as the other techniques, but also as we are measuring around a Bragg diffraction, we can obtain also information about the displacement field. So the displacement field will give us information if the atoms are displaced from the ideal position in the crystal. So we're going to have this information from the displacement of the atoms. We can also obtain information about the strain of this network. And why it's important? Because in catalysis, so here it represents a relaxed crystals. When you have a tensile strain in this crystal, we're gonna have a depend effect because these atoms are, we have more free space between them, then they can share, they have more, it's easier to them to share the electrons. So it's really likely that the reaction, the catalytic reaction, is gonna occur in this region because we have the electronic structure more prone to make new bonds. And when we have a comprehensive strain in this crystal, it's the opposite. So changing the strain of the nanoparticle will change the electronic structure, and for consequence, it's gonna change the energy of absorption and desorption. So when we have this condition, this tensile strain, it's have been shown by experiments and also simulations that it's likely that the reaction, catalytic reaction, it's gonna occur in this region. So for this study, we using a model reaction, actually it's the CO oxidation, very simple reaction. We analyzed the coating nanocube. We put this mixture of CO and oxygen in the reactor at room temperature. As we increase the temperature, we can observe also, it's here. The red region is the tensile strain. Increase the temperature, we can observe the red region, the tensile strain, in some preferential locations in the cube. So we give us already information about the activity of the different facets. Sorry. And then we follow the samples during heating and also during cooling. And what was interesting to note is that we heat the sample at 300 degrees. We do not have any tensile strain on the particle. Then the tensile strain is formed at 400, that we already know it's the maximum of the conversion. When you cooling down, we have also tensile strain at 300 degrees that do not observe during the heating. And then the nanoparticle come back to almost the same condition than the beginning. And what was interesting, because in the sample, we have a hysteresis. So if during the heating, have this conversion, and then during the cooling down, we have this hysteresis. And if you observe the point of 300 degrees where the reaction starts, the conversion starts, during the heating, conversion is really, really small. And during the cooling down, it's much higher compared to the same temperature. What we observe in these studies, with the temperature, the reaction starts, we observe the region of the tensile strain that should be where the active sites are located. Once they are formed, they stay a little, they have, once they are formed at 400 degrees and we start to decrease the temperature, they're still there. So it's why we have more conversion during the cooling cycle than the heating cycle. It's harder than to form. Once they're formed, they have like, I don't know if we can call this a long life, because, well, anyway, it's not a long life, but they remain some time once they are formed. And then it was nice because we could understand better this behavior of hysteresis, because in the literature, it's well known for this catalyst and these reactions, but usually people always say that's related with the temperature offset, the reactor, but they never, there's was not a relationship with the single particle, with the structure of the catalyst itself. So in this work, you could see the defect dynamics induced by the reaction and the formation of the preferential activity site. Here it's another particle, the same work. In this case, it was a cuboctahedron. And to make it easier to visualize, I'm just showing here the maximum of the tensile strength in red and the maximum of the compressive strength in blue, but we're interested in the tensile strength. This particle presents an inverse hysteresis than they showed before. So here I have heating and cooling, and here it's the inverse, heating and cooling. And if you observe with the temperature, we observe this increase of the tensile strain through the particle that will increase and achieve the maximum at 400 degrees. And once I started to cooling down, it started to vanish in these regions. So to understand this hysteresis, what we did, we calculated the elastic energy as well of this particle. And it was really interesting because we could observe in the single nanoparticle scale, we also have hysteresis in the elastic energy. So with this evolution of the strain in the nanoparticles itself, that will induce this hysteresis behavior. So we could see that the activity catalytic is related to the elastic energy of the nanoparticle. And, well, that changing this strain, we can control this the catalytic activity of the nanoparticle. As it's really, it was like really nice results, new results, and we were really happy to publish this Nature Communication because we could show in the level of a nanoparticle how nanoparticle is reorganizing and how it's related with this hysteresis behavior that's before was thought to be related only to the external conditions like temperature, like the kind of reactor, and you could show in this study, no, this also observed in a single particle. It's related, and how these tensile strain regions are formed and how long they stayed in the system. Another example that's really nice to visualize better the capabilities of the Bragg CDI techniques, and it's when you have a huge defect on the sample. So, for example, you can have this twin defect. So here we have the crystals, C, A, B, C, and at some point we had a defect and it's changed the sequence, and then the plane will grow in another direction. At some point, it come back to the original sequence and it's growing the same direction again. So this is called the twin boundary. It's well known to happen in metallic nanoparticles. Here in the electronic transmission image of a seed that we use to grow this particle, we could already see twins. And when we grow the particles and we look at the electron microscope, well, we could not see because it's large particle. So we do not have resolution to see these twins. But when we went to the beamline and we measure Bragg CDI, we have this funny shape. But believe me, this funny shape corresponds to this sample. What happens is we align the detector to obtain the diffraction pattern of the sample. Once this twin is formed, it will diffract the X-rays in other direction, not the detector. Then I have this empty space. In this region, not the twin region, it's diffraction again, it's diffracted on my detector, and I have this information. So we have this funny profile, but it's not that it's missing, but it means that it's aligned in another direction. And twins are known to have a good effect on catalysis, and we also studied these twins during the reaction. And it was interesting to observe that when the reaction starts, here it's the operandi results during the reaction. So it starts around 300 degrees. The reaction itself induced a tension in the boundary of the twins, and we have a movement of these twins during the reaction. So you can see a different movement of these twins, and then when the temperatures, when the reaction is finished, it's come back almost to the same particle that I had before. And in this picture, it's comparing the shape of the initial shape of the catalyst and the shape of the spent catalyst when I have this rotated, this twin that is rotated in and out of the Bragg condition, and we can follow this using Bragg CDI. Well, we still have 5 minutes, but I just show a little bit more information about the experiment itself. Bragg CDI is in commission at Carnaúba Beamline. It is still not available, but I think it's going to be available soon. Plane wave CDI is under commissioning at KTRT and should be available soon. And tachography is available at KTRT. So here shows some examples. It's like old results. Hopefully now my video is working. So this is some zeolites and cubes. Here it's a material composed by its nanospheres of copper microspheres of copper supported on aluminum. So this is the image of electron microscope, and using this tachography technique, you always have a really nice contrast between the different electronic densities. So you can clearly see what the copper spheres and what are the alumina subparts. So about the experiment, almost the same configuration of XPCS, but the main difference is for this image techniques, we use this online microscope that's very important to align the sample. So it's located on the beamline, the X-rays goes inside it, and we put our sample in a membrane. And we can use this optical microscope to visualize, then we can choose what candidate we're going to analyze and to align the center of rotation for the tomography. So for the CTI experiments, the most challenging part is sample preparation. So here, cannot see very well, but we have 4 candidates on this membrane. So it was this microspheres, some catalyst as well. We have to obtain isolated samples because of the tomography. You need to be able to rotate it without have any other object in the view. And we are using the silicon nitrate membranes because they're transparent for X-rays, so it's quite nice. Radiation damage can be a problem. As I told you, it's a long experiment. And for it, we are also commissioning a cryostat to be able to do these measurements at low temperature and then mitigate radiation damage. At the beginning of the experiments, we need to align the sample because to have this tomography, the sample should be very well aligned. And as for XPCS, we need to be able to see the results quasi in real time to take the decisions. So, but in this case, what we do, we obtain the 2D image, we reconstruct it, and then we have the 2D. This it's quite fast because then to reconstruct the tomography, we need more time. But during the experiment, we obtain the 2D image because then the user can look at the image and can say, oh, it's okay. I think it's a good candidate, or oh no, it's not okay. We should analyze another one. And once we decide there's a good candidate, we go to the tomography. Well, so to close this presentation, I would like to do an update about the beamlines that are open for project at Sirius. So we are located here, Caterete, the second longest beamline. It's open for project. Carnaúba, that is dedicated to the nanoimaging and fluorescence. It's open as well. In Buia, it's the infrared beamline. EMA is the beamline dedicated to extremely conditioned experiments, high pressure, temperature, they're performing diffraction, absorption. The Manacá, that's dedicated to protein crystallography, and also IP that perform XPS, and they're also commissioning rigs. So as I show you, there are some, for image, for example, sample preparation, it's much more challenging. And for XPCS, challenges to find the conditions to start the experiments. So here at Sirius, we have tools to cover the whole workflow. So for the sample preparations, we have some support labs that users should talk with the beamline, the local contact before to talking about this. We also developed samples to collect it and reconstruct and analyze the data. Well, I hope that with this class I could give you some idea about these new possibilities at CDUs, how we can use this to study dynamic and structure, and I hope I can see you someday here at CDUs measuring at KTRT or another line. It's gonna be a pleasure. Thank you.
Muchas gracias, Aline, por tu presentación muy bonita. No sé si alguno de los chicos tiene alguna pregunta para Aline.
Okay, no problem. If you have any questions, you can send me an email. If you are interested to submit a proposal for KTRT, you can also send me an email and we can discuss about your system. So feel free to contact us and any other staff here in CDUs if you're interested in these new techniques and you think it could be nice for your system. I encourage you to contact the local the beeline scientists and discuss about these opportunities.
Muchas gracias, muito obrigado, Aline. Ok. Depois eu pego aí o arquivo para pegar toda a reunião junta. Você tem uma pergunta aí de Paula. Can you use hydrogel as sample in the pictography technique?
Here you face the same problem of excision. You can face it, radiation damage. So for tachography, as it's a scan technique, the measurements are quite long because we will scan the sample to obtain a 2D, then we rotate and we scan again, rotate and scan again. And usually you have to collect at least, depends on the size of the sample and the resolution you wanna reach. But sometimes we need to obtain, for example, 500 projections. So it means that your sample will be scanned 500 times. So it depends how long your sample can survive on the beam. Even though for tachography it's a small beam, because as you see here in this picture, we reduce the beam size. Here at KTRT use a